6.6 kilowatt onboard charger with gallium nitride using C2000 real-time microcontroller unit. So the outline of the presentation is I'll be discussing about the project source, converter topology, and control objectives. And my friend Anirudh will be discussing about control methodology, code generation model, and summary. And regarding the project source, we have given the link to the YouTube video and the link to the source file and designs file of our project. So what is the reason for selecting this project? This onboard charger is mainly used in electric vehicles, and since our course mainly focuses on electric vehicles, we have chosen this topic to be discussed. So this picture in the left hand side shows the back view of the onboard charger and the right pic shows the front view of the onboard charger. In this picture, the green module is the microcontroller mounted on a PCB board. So now we'll be talking about the simple schematic of the onboard charger. From the left hand side, a single phase supply is fed to a totem pole power factor correction circuit, in which it uses a capacitor to convert a single phase supply to a three phase, which has phase difference of 120-degree leading from each other. This AC supply, three phase AC supply, is fed to a 6 MOSFET circuit which rectifies AC supply to a DC, and the DC is being inverted back to a AC supply using a 4-bridge MOSFET. Then the output of the 4-bridge MOSFET is given to a CLLC circuit, which means capacitor, inductor, 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 capacitor circuit, which is a star connection circuit. The output from this circuit is being inputted to the 4-bridge MOSFET, which converts the AC to a DC. Now we will be talking about the converter waveforms. Here we have seen three waveforms. In the first graph, it is the graph between output power and the efficiency, in which we have two parameters for both biased voltage and unbiased voltage. And in the second graph, we show the efficiency for CLLC. And for the third one, the graph shows the efficiency versus output power for a system efficiency. The first graph, the unbiased efficiency reaches up to 98.5%, and for the CLLC, the efficiency reaches up to 98%, and for the system efficiency, it reaches up to 96.5%. So now what is the final variable to be controlled? The final variable to be controlled is the overall system efficiency, but that is purely dependable on PFC efficiency and CLLC efficiency. So what is the need for the control? To get the maximum efficiency possible using a converter system with PFC and CLLC as its component. So now we'll be talking about the control system description. The design employs a two-phase totem pole PFC and a full-bridge CLLC converter with synchronous rectification. The CLLC utilizes both frequency and phase modulation to regulate the output across the required regulation range. The design uses a single processing core inside a microcontroller to control both the PFC and CLLC. The next part will be explained by my friend Anirudh.
Thank you, Ashwin. So the control methodology, the code generation model, and summary will be explained by myself. I'm Anirudh. So let's talk about the overview of the controller. The design we are using is a PMP22650 reference design, which has been created by the Texas Industries. Um, this is an onboard charger with a 6.6 kilowatt bidirectional ways. The Like my friend Ashwin said, the design uses a two-phase totem pole PSC and a full bridge C-triple-LC converter with synchronous rectification. The synchronous rectification is implemented via the same microcontroller with Rogowski control current sensors. High density is achieved through the use of high-speed gallium nitride switches, which are semiconductor devices. The PFC operates at 120 kilohertz, and the C-triple-LC runs at 200 kilohertz to 800 kilohertz. The peak system efficiency is 96.5%, achieved from the open frame power density of 3.8 kilowatt per liter. The 96.5% peak efficiency of the system is achieved by achieving 98.5% peak efficiency of PFC and the 98.98% peak efficiency of the C-triple-LC. While we have done the design calculations for 6.6 kilowatt output power, the design represents the suitable starting point of 7.2 to 7.4 kilowatts, and the rated OBC operates at a 240 volt input and 32 ampere breaker. Now let's see some of the code snippets. This is the main block, part of the main block, which shows the AC connected to AC supply connected to the totem pole, two-phase totem pole PFC, which is in turn connected to C-triple-LC, which full bit C-triple-LC. The C-triple-LC has different ports which are connected to it, and these ports are supplied by the bias voltage of 12 volts. And here we can see the U1 and U2 subsystems are converting the C-triple-LC secondary side parameters to battery side parameters and ground parameters. Uh, and the U2 converts C-triple-LC secondary side parameters to VSNS input parameters, which is the voltage source input parameters. This shows um, the uh, this shows the bias voltage and the effects of bias voltage on the U1, U2, and T1, T2 transformers. Next, we will talk about summary. The summary in this project, in this presentation, we have seen about the converter topology, controller objective, methodology, and some of the code generation snippets for 6.6 kilowatt onboard charger with a gallium nitride semiconductor C2000 using C2000 microcontroller units. The references are from the Texas Industries. The link to the YouTube video and the link to the source files and design files are given here. The link to the source files and design files is the same as the Texas Industries official website. Thank you.